for this heat to go through, and this window is supposed to be area. So now we get an idea, hopefully, of what this thing is. It says the heat flux density at a point, and actually the window should be at the point, but we won't worry too much about that. It's how much energy flows through a meter squared area in 1 second. That's what it is. Now what that means, it means a few things. This would be per meter squared. It means a few things. If you leave the hob on for a long time, while you're getting more heat transfer, the density is the same the whole time. And if you double the size of the hob, okay, you've got twice as much heat being transferred, but as a density per meter squared, it's actually the same. Okay, I appreciate this is a difficult thing, but hopefully it might help something in your well, I don't know what thermofluids is, but certainly thermophysics. Right, we got it. So, this vector, the heat flux density, as I said, is not uniform. Say at the bottom of the hob, it's very, very large, and over the handle, it's small in a different direction. So here, for example, at the bottom of the pot, the heat flux density might be large in the K direction, while at the handle, it might be small in the I direction. To describe what it is, suppose that the heat flux density was uniform. Okay? Suppose that the heat flux occurs only in the X and Y directions. Now that is good for our plate because say if this is X and this is Y, we're not having heat transferring between the top and the bottom of the plate because it's so narrow. So this is just going to repeat almost exactly what I said, I think. So here's your, this is just writing what I wrote on the previous page, to be quite honest with you. So we have a point here, x0, we can forget about z now. And suppose that the heat flux density is the same everywhere. It's not. Now that's actually something that you have seen before in a different context. What is instantaneous speed when you hit 100 kilometers per hour in the car? What does that mean? Well, what it means is if you have that speed everywhere, and what that means at all times, how far would you go? It's a similar thing here. You're saying, okay, what is the flux density at a point? Well, imagine if the flux density was the same everywhere. For velocity, it says, oh, the instantaneous velocity is 100 kilometers per hour. What that means is if I'm always at 100 kilometers per hour, it means that in 1 hour I will go 100 kilometers. So we have a similar story here. So imagine the heat flux density everywhere is the same. Even though it's not, it's actually variable. Now, I think what we're going to do, what are we going to do? So, consider the amount of heat energy transferred into unit area in 1 unit of time. These joules of energy enter either through the vertical face or the horizontal face. And the total energy through the vertical face is Qx, while the total energy through the horizontal face is Qy. Now, why is that? Well, that is because this vector is composed of heat transfer in the X direction and heat transfer in the Y direction. And the interesting thing, I suppose, we'll see it in a moment, the heat transfer in the X direction actually goes through a kind of a Y face, as it were, and the heat transfer in the Y direction goes through an X face. We'll see this in a second. So anyway, this is the rate of transfer of heat per unit area. Rate is where we get our per second. Okay, so we got this kind of a jobby. So now let's think about our volume element. I say projection because we're not going to worry about its thickness. And what we're going to do, we're going to make an assumption that isn't a good assumption, but it's valid if I manage to make the mesh very, very fine and the little squares very, very small. And I can always do this theoretically anyway. So, what we're going to do is we're going to have heat flux in, heat flux out. Now I've drawn the heat flux in a suggestive way. Obviously, if we had just hot and cold, it'd be just going this way. I'm saying that basically the overall story is it's going from here to here. So this might be something like, if you've got the big plate, it's kind of hot down in the corner, cold up there, you're going to have heat flowing in this direction. Right. Now let's write down these two vectors. And let's write down some coordinates. So this is actually that doesn't matter. I'm just going to write down stuff. So the heat, that's a vector. I'm going to draw an arrow in. The density in is equal to, so I'm going to say Q of xi plus Q of y j. Now what I'm assuming, it's kind of, the assumption I'm saying is that I can basically capture the fact that the heat flux density is changing by saying it's got two values, the value here and the value there. It's a little bit dodgy, but you can fix it with heavier maths if you need to. We don't really need to. Now, what is the x and the y corresponding to? And it actually suggests something about, I was talking about this x0, y0, z0 notation. Now that I think about it, it actually, it shouldn't have been the case. So this is correct. Now, the heat flux density out is equal to, now, the x coordinate is now x plus delta x, because this is delta x and this is delta y. So this is now, over here, the coordinate is x. Okay, I have to write something else here. So this coordinate is x, y, is what we're taking it of. And this coordinate here is x plus delta x, y plus delta y. And so the heat flux density vector coming out here is Q of x plus delta x I plus Q of y plus delta y j. Right. So what we want to say now is how much energy goes in and how much goes out, and we want these to be equal. Okay, now the way we said that the heat flux density is how much energy passes through an area. Now this doesn't look like an area, but if we included the delta z, it would be there. So basically this delta x is, look, I'll throw in the delta z. So, how much heat is in a certain amount of time? So how this works, right? The Q of xi goes through there. The area is delta y by delta z. And we're saying in a certain amount of time, delta t. So the heat in we get is Q of x, so that's the heat flux density in the x direction, times the area, which is delta y, delta z, times the amount of time. But the idea is, okay, this is a heat flux density, this is a heat energy per meter squared, so per area, per time. So multiply it by area, multiply it by time. This is the amount of heat that goes through that face. You've also got heat going through the bottom face. And now you've got heat going out as well. So you've got heat going out this face here. It would be Q of x plus delta x times delta y, delta z. To get that to make an area delta t, plus the heat energy that goes out the top. Right, so this is deriving this equation. Okay, this can be arranged, so this is kind of easy enough. Divide everything by delta z, delta t, that's gone. What do you do then? Maybe divide everything by delta x, delta y. Then get all the, look, it's just an algebra problem you get to here. So this is an equation that is a consequence of heat energy in, heat energy out. So this is an equation that the heat flux density describes if heat energy in is equal to heat. In other words, this is steady state. Okay. Right. What have we got here? The problem with this is that it assumes that the heat flux density assumes only two values. We said this. We used to. That's wrong. This is not true. However, the heat flux density should be continuous. And what that means is if you make the volume very, very small, a very, very fine mesh, there's very little difference between these two. And this is the same as making delta x small and delta y small. And here I mean mathematically small in the sense of limit as they go to 0. So we end up with this. So this is a more accurate thing. Now it's still actually, if we think about it, only using two values, but it is far more accurate. You can be convinced of this completely. This is a derivation. It's not a perfect mathematical one, but it's pretty good. Right, now the question is, what the hell is going on here? And this you should recognize if you watch the finite differences, or you should just recognize this anyway. These are derivatives. Change in flux density over change in x, change in flux density over change in y. Now the thing that's a bit more interesting about them than before is that when you look at this one, so this is x is changing, and in this case when x is changing, y is kept constant. And so this is the rate of change of the heat flux density in the x direction when y is kept constant. And if you think about derivatives when other things are kept constant, these are actually partial derivatives. So this thing is the partial derivative of qx plus the partial derivative of q with respect to y equals to 0. So I would say that how are you getting a partial differential equation? Well, we're considering changes in a variable q. Now there's other things are kind of under the carpet here, but it doesn't matter. But basically we're looking at a change in x and y doesn't change. So that's differentiating with respect to x and y is kept constant. That's partial differentiation. And so is this. So they're just kind of coming out of the woodwork because we're looking at the x direction and the y direction almost independently, but they're not independent though, because they form part of the one equation. So this, usually when you've looked at partial differential equations, or excuse me, partial derivatives, you're just looking at, you're not considering relationships between them, but here you are. This is a partial differential equation. It has good, easy answers. So for example, if this was say 2x and this is 3y, that would be solution. The problem would be, and this is what you'll meet in fourth year, how to satisfy the boundary conditions, and that won't satisfy the boundary conditions unless you kind of make it that way. Right. Now, what we promised was, like, you don't actually know much about heat flux density, so what you're more interested in is temperature. What is the temperature distribution of the plate in steady state, so when everything is actually settled down? So what we need to do is look at Fourier's law of heat conduction, which we've actually mentioned already, which says something like this. Consider this to be a face. This would have a width delta y, I think. And consider 2 points. So say x and x plus h. And basically, okay, the units, in this case, the units, I don't know about that. It says, no, that should be per meter squared, because this, it has to have an area. You can't have heat going through a line. That doesn't work. So there's a little bit of delta z going on as well. So it's just a very, very narrow thing there like that. That's a crap picture. That should be like a little narrow pane, a window, okay. So, what Fourier's law of heat conduction says that the heat transfer, the heat flux. Now, if you drop the density, you don't worry about the per time element. So it's a different thing. It says it's proportional to the temperature difference. So you get a big heat transfer. It's not a million miles away from Newton's second, or Newton's law of cooling. So this would be Q of Xi. And it says this is big if the temperature difference is large, in particular if this is hot and this is cold. So what we see is that the heat transfer, I'm a little bit worried about time. There, we won't worry about the time. We'll just write this down. So it says that this is how much heat goes through per unit time, whatever. This is heat. It's missing a bit of delta Z, but we won't worry about that because I think actually we'll put in the delta Z because I think I can divide it all out at the very end. So throwing in all delta Z here. So this is the heat transfer through this little window is proportional to the difference in these temperatures. And in particular, to get the right sign, this should be minus. So through now the X is turned into a Y, and this is why I said originally that I need the delta Y to be the same as the delta X. So it has to be a square grid. So the delta Z is still here, and there's a delta Z still here, that's okay. So this is saying that the heat, this is basically a way of saying, okay, the heat flux density is basically related to the difference in temperature. Again, this assumes constant heat flow. To be more accurate, we take these points to be closer and closer together. We do the limit as delta X goes to 0. And as we do the limit as delta X goes to 0, we, I think, end up with Q of X, and again, we're moving in the X direction, not in the Y direction, so we have a partial derivative. I think I'm going to get minus K dashed, and the delta Z can come out as a constant this time, and then what you see here is a partial derivative of temperature with respect to distance along the X. A similar analysis in assuming isotropy. What isotropy means is that the heat transfer in the Y direction is the same, in particular this K is the same. The delta Z will have to be hanging around again. And so if you throw this up into this, dividing by K and multiplying by delta Z, we end up with the following equation for the temperature. The second derivative of temperature with respect to distance, partial derivative, plus the second derivative of temperature with respect to vertical distance is equal to 0. And this is the partial differential equation that governs the temperature of an insulated plate. This is the steady state. If it's three-dimensional, you have the extra term, but we don't need to worry about that now. So what we're going to do in week 9 is look at how do we estimate solutions of that differential equation. How much of these little series of videos is examinable? We will come back to this a bit later. Okay. Thank you.